So we have seen how to fit linear models to linear data in Python and in PyTorch. So we can do linear regression in PyTorch. Perhaps you're thinking, well, maybe we didn't need all of this fancy programming, all of these terms just to do linear regression. We could do that before. And perhaps I would agree. But the beauty of the thing is that now we can feed models to our data, and that we can feed, using this fit function that we have defined, many models to different types of data. At the start of the notebook, we defined linear data and quadratic data and even cubic data. And so far, we have just used a linear model to fit to linear data. Again, not super exciting, but interesting. Let's try to feed some linear model that we had to some quadratic data, and as you can see, not much happens. So perhaps this is not that surprising. We wanted to fit a very simple model, a linear model, to data that was not as simple, that was quadratic, and it didn't work. What do we do in this case? Well, we need to do something else. We need a more complex model. We need, for example, a quadratic model. In order to do quadratic regressions, well, you can learn other formulas, you can learn other procedures, other equations, or you can just define a different model and use the same fit function that we already defined before. We will use this same fit function that we had already defined, but we will change the model. At this point, instead of having just two parameters, A and B, we will have three, A, B, and C. The second degree coefficient, first degree coefficient, and independent coefficient. So let's define this quadratic model. And now let's just fit this quadratic model to our data. As you can see, fitting this model, even though we are doing 15,000 iterations, doesn't take long, because PyTorch runs using the GPU of the computer. In this case, it's using the GPU of the computer in Google Colab, which is not a super fast GPU, but it's good enough. And now we just fit. We fit it here and we plot the fit, and the plot is, again, very, very, very good. PyTorch and this fit function that we defined in very little time and in just a few lines allow us to fit linear models, quadratic models, and any model that we can define. We defined at the start of the notebook cubic data. Okay, and I'm sure you can see how you could define a cubic model and fit it using the exact same function. Okay, to solve this, you would need to just change this quadratic model definition to a cubic model, and then initialize its parameters. Now you would need 4, because cubic models have 4 instead of 3, and call the fit function with a cubic model and the cubic parameters and the cubic data. Okay, but this is left as an exercise, and if you know some programming, you can come and do it. Even if you don't know a lot of programming, I think this should not be very difficult, having these examples. And the beauty of Google Colab is that you can run all that code without having to install anything, just run it from your web browser. As I said before, we are going to use these same ideas to fit really, really complex models, deep learning models. But before we do that, let's just do an intermediate step. Let's define how to fit a model that represents a fine transformation. Okay, this comes motivated from some research that I have participated in medical imaging. There, very often the anatomically important regions that are visible in the images are marked by experts using some points that delimit the boundaries. So you end up having a collection of points that represent some polygon that more or less encloses the part of the image that we want to see. I don't know, tumor that's visible in a breast image X-ray, or the left ventricle of the brain, or the cerebellum, or whatever anatomically important part is shown. And sometimes we want to register the images, so move all of those images taking into account this information of where these important anatomical regions are. To do that, we want sometimes to transform one set of points showing these regions into another. So what we are going to do here is just generate some data that generates and plots three simple squares. So let's do just that, okay? And we end up with the data for our problem. Oh, sorry, I forgot something. Let me check. Yep, I forgot to run the affine transformation. Again, beauty of the code is that it gets errors, and we can show it here, okay? So in short, and you can check the details of the code, they are not super difficult. You can check them if you are so inclined. We have basically generated two squares, and we want to transform using an affine transformation one onto the other, okay? And the point is that affine transformation can be used as matrices, 4x4 matrices. 2D affine transformations can be defined from a rotation angle and a translation vector as 3x3 matrices. You can check that. I will add some references to the comments of the video, but basically any affine transformation can be defined in this way, from an angle of rotation and translation vector tx and ty, and then we have this 0, 0, 1 in what are called homogeneous coordinates. You can check all of that out, right? The main point is that now we have a way to transform one square into another square. So that's what we will define as our model in this case. Our model will not have 2 parameters or 3 parameters like we have been seeing so far. It will be a whole matrix of parameters. That's not a big matrix, but it's bigger than the one that we have been using so far, the models that we have been using so far. And we will use the same procedure that we had been using so far. First, let's just play everything randomly, and you see that the 2 squares that we used to have are there, but the initial transformation transforms one into, well, not really the other, but something else, okay? Now we just have to define the parameters for our transformation like we did before, defining some random parameters, and fit, using the exact same fitting function that we have been using, this new model, the affine transformation, to our data. Again, doing 15,000 epochs, but because of the GPU, the thing does not take long, and you will see how, after the fitting, I can plot it, and now I only have 2 squares visible. My squares used to be this small one and this one here, and now I have managed to move. So first I had the 3 ones, the 2 original positions, and my model somewhere here, and now my model, this red square, is exactly over the bigger square because I have found the way to transform this smaller square using an affine transformation into this bigger square. Okay, so that's it for now. Basically, we have given an intuitive idea of what a model is and what it means to fit it to our data. But we have then explained how the fitting process worked, and we have spoken about loss functions to know at each step how far the model is from the data, and how fitting the model means optimizing, finding the minimum of that loss function. To find the minimum of any function, we compute its derivatives, and if the function have more than one variable, they are called not derivatives but gradients. PyTorch does that for us. Computing the gradients of big functions like we have can be very complicated, but PyTorch does that automatically for us. We have defined a fit function to tell PyTorch what our data is, what our model is, and how to compute the fitting of that model. We have seen examples with linear regression. We have fitted linear data using a linear model. We have seen that if the data is a little bit more complex, it's quadratic, we cannot fit linear data to it, but we were able to define a quadratic model, and we could do any sort of polynomial model using the same approach. We have even gone a little bit further and into the practical, using this fine transformation model to fit one square into another, using this affine transformation. And as you will see in following videos, we will follow the exact same approach to fit deep learning models to complex data to solve very, very complex problems. And that's it. I just want to finish saying that at some point we delved a little bit deep into the math. Deep learning has become super popular, and one of the reasons is that it can be used as a black box. So you don't really need to understand the math to use deep learning to fit some models to some data. You have plenty of tutorials, and we will give another one here too, to fit data to models. Even super complex models, some of these deep learning models that do super amazing things. However, if you are able to understand the data, you can become a much better user of the technology, because then you will understand why sometimes things don't work as maybe you think, because the intuitions are great, but they don't always work. The black box is amazing and does lots and lots of things without having to understand much of anything. But if you do understand, you can do even more. So let me just encourage everyone who is interested in this to learn to code. It's another way of thinking, and it's not as difficult as you might imagine. I would say it's plenty easy. There are lots of kids, very young kids, near where I live. Kids are taught to program from age 4 or 5 sometimes, okay? So give it a go. You have the videos, notebooks, slides, different contents here in this course. For example, if you want to try it, there are many others if you don't want to. And if you already know some coding and so on, get into the details. If you are here for hard PyTorch code, here you have it. The fit function is essentially, this very simple fit function works essentially the same way that fit functions for deep learning models always work. And stay tuned for the next video where we will show exactly that.